All right, so the next thing we're going to take a look at, which is just an extension of stoichiometry, is the idea of limiting reagents, and some other concepts that kind of flow from that. So just generally, when we talk about limiting reagents, sometimes it's called limiting reactants, or just sometimes they're abbreviated as LR. Okay, what these are reagents or reactants that limit reactant that limits how much product is made. Or how much product can be made. Okay, and the other characteristic of a limiting reactant is that the LR, the limiting reactant, is used up in the reaction. So in other words, there's none left over at the end. And once it's used up, the reaction stops. Okay, because once it's done, once it's used up, it limits or puts a cap on how much product can be made. So let's take a look at an example. We'll use the same reaction we've used previously, N2 plus H2 to give NH3. We have our balanced equation. We need the 2 and the 3, and then remember we have 1 in front of the N2. Okay, so now let's change the question around a little bit. So let's say if you start with 1.5 moles of N2 and 1.5 moles of H2, how much NH3 ammonia can theoretically be made? Okay, so here we're told instead of just giving us one of the amounts of one of the reactants, we're given both of them, right? And we need to figure out, well, how much of this, the product here on the right side, can we actually make if we start with a certain amount of the N2 and a certain amount of the H2 given in moles. So when it comes to limiting reactants and figuring out, so the other question here we can ask is, what is the limiting reactant, the LR? And then we're going to also ask what is in excess. In other words, what is left over at the end? Which reactant is in excess? And then obviously we need to find the theoretical yield. Okay, what is which is really just another way of restating the first question. Theoretical yield here is often abbreviated as TY for theoretical yield. Okay, so when it comes to limiting reactants, limiting reagent problems, you're going to have to do multiple stoichiometry problems. And in this case, because we have two reactants, we're going to be doing two stoichiometry problems, right? So we start with each of them. So we'll start with the 1.5 moles of the N2. And then because we need to figure out the NH3, we're going to relate each of them to the NH3. So in the case of the N2, it's a 1:2 ratio. So 2 moles of NH3 are produced from every 1 mole of N2. Moles of N2 go away. 1.5 times 2 is 3 moles of NH3. Okay, so that's the first calculation. The second one then is to take the other reactant, the 1.5 moles of the H2, and we do the same thing, figure out how much of the product we can make using the mole-to-mole ratio. So 2 moles of the NH3 are produced now from every 3 moles of the H2. Okay, moles of H2 cancel. 1.5 times 2 is 3, divided by 3, we get 1 mole of the NH3 is produced if we use up all of the H2 instead. So once you do your calculation, both multiple of them, so starting with each of the reactants, we figure out how much product each of those reactants can make if they were both individually used up, and then we just compare. And then the smallest, or the smaller of the two in this case, is going to be the theoretical yield. So that's the 1 mole of NH3. Obviously, 1 is less than 3. And then the reactant that produced, or the reactant that gave the theoretical yield, is going to be the limiting reactant. So in this case, the limiting reactant is going to be the H2. And if the H2 is limiting, that means the other reactant, which would be the N2, would have to be in excess. Okay, abbreviate excess as XS, which means some of that is going to be left over. So if we were to run this reaction, all of the H2 would be used up, and we'll have some of the nitrogen left over at the end, and we should theoretically get 1 mole of NH3, right? So that's our theoretical yield for this problem. So again, it's stoichiometry. It's the same calculations you're doing, but now you have to do multiple sets and then compare the answer. Now, when you do calculations like these, this is in an ideal situation, right? If everything worked out perfectly, you should get 1 mole of ammonia. So let's say if we actually carry out this reaction, so if this reaction was carried out and let's say 7.9 grams of NH3 was experimentally obtained, what is then the percent yield? Percent yield for this reaction. Okay, and this is the other concept we need to consider now is the percent yield, right? So we looked at several of these concepts you would have seen before. So we talked about limiting reactant, we talked about excess reactants, we talked about theoretical yield. The last part of this is the percent yield. Okay, and the formula for calculating percent yield is always yield is the actual yield that you get from doing the experiment. So actual, sometimes it's called the experimental, divided by the theoretical yield times 100 because it's a percent, right? So we just need two numbers to actually do this. How much did we get from doing the experiment compared to how much we should have gotten from doing the experiment? Well, we calculated the theoretical above, right? So 1 mole of NH3 is what we should have gotten. Okay, and we can convert that to grams using the molar mass. So 1 mole of NH3, nitrogen is 14 plus 3, so that should be about 17.02 or thereabouts grams of NH3. Right, so I've converted the theoretical yield in moles to the theoretical yield in grams. So that's 17.02 grams of NH3. We are told down here that you actually got 7.9 grams. That's your experimental yield. So I can just take those two and divide them. So 7.9 grams I actually got divided by how much I should have gotten, 17.02 grams, times it by 100. Okay, and then whatever number I get there, that's going to be your percent yield for that reaction. And all of these ideas and concepts are really important because you're going to see them all the time. You'll see them in this class, Gen Chem 2. If you go on to organic chemistry later on, you will do a lot of those as well when you do your experiments in the lab. You will have to calculate theoretical yield, percent yields all the time. So it's really important that you understand the terminology. It's really important that you understand just generally how to do stoichiometry, right? You need a balanced equation. You need to have your molar masses if you're starting off with mass, for instance. And the goal for any stoichiometry problem, what's at the center of every single one of those is you have to get to moles.